Hi, welcome to lecture 3 part 2. We are going to talk about the kinematics. Kinematics is the study of the motion of the object. That motion can be a rotation of the object, can be a velocity, or can be acceleration. So, in inertial navigation system, we always have a body or object, which can be UAV, which can be vehicle which carry laser scanning, it can be, for example, airborne vehicle, carry LiDAR, so all those things can be counted as inertial navigation system. So we're always dealing with three reference frames. The first frame is the object frame or B frame, we will call it alpha in here. The next one, we are talking about the frame in which the motion is in respect to, which is beta, in our case is inertial system, or we call it I frame. And then we have the set of axes in which the motion is represented, which we call it gamma. So to simplify that, we have object reference frame, we have inertial reference frame, and then we have a desired reference frame or G frame that we want to get the answer in this frame. Let's start with the rotation. We can call rotation angular rate. What angular rate shows you is the rotation of the frames relative to each other. In this case, for example, I can show you the rotation of the alpha frame, which is moving frame or object, in relationship to beta frame, which is the reference frame, in our case is inertial frame or I frame, resolved in the desired frame. So if we want to represent this motion in another frame, we can write it in this form. So as you can see, I have this rotation matrix, which is the rotation of alpha with respect to beta resolved in the desired frame of gamma, and we want to show that in the frame of alpha. Because this is a vector, and as we described the schizometric equivalent of vector, we can simplify that as this one here. But in a kinematic sense, we are more interested to see how the frame beta is changing over the time in relationship to alpha. So I want to see the relationship between the beta and alpha, which is changing during the time. This means that if I know the relationship between these two reference frames at time 0 or to start with, and if I know the angular rates in one frame, then we can calculate this derivative with respect to the time, and then we can multiply that to the delta t or the time period to get the change in the relationship of those two reference frames that occur during that time period. The next kinematic element is velocity. Velocity is the rate of change of position. So if you have two reference frames, alpha and beta, beta is inertial reference frame, alpha is object, and if one of them is moving in respect to another, then you can show the rate of change of the position of the first origin. So I have two reference frame. Good. If I call this one alpha and I call the other one beta, so the rate of change of the position of their origin in respect to each other can be shown by velocity. Velocity is simply the time derivative of the position, which can be shown by this formula here. Remember, you might have either frame working, like I might have frame alpha stationary and B is moving, or I can have beta stationary and alpha is moving. So either frame can move. But more than this, remember the velocity also shows the rotation of one frame. So this frame, for example, as it moves, is also rotating with respect to frame alpha. So we have to consider that rotation. So to account for that rotation in physics, we can add another element to the previous formula we had, which account for the rotating of frame alpha with respect to the beta. The second part of this equation shows you the movement of origin of two reference frame alpha and beta. The first part is basically accounting for the rotation of the reference frame alpha with respect to the frame beta. The third element of kinematic is acceleration. How we can show the acceleration? Simply the time derivative of velocity is acceleration, which is gonna be the second time derivative of the position. If you kind of remember from the previous slide, the v, so v of our velocity was the time derivative of the position. So if I'm getting the second time derivative of this formula, it's gonna give me the acceleration. So again, the rotation of the frame will also affect the measured and apparent acceleration in each frame. So the acceleration is not constant, as the frame is also rotating and moving, so it's changing the acceleration. We have to take into account of the rotation of those two reference frames, which can be written as this one. Again, the rotation of the frames will have an effect in the acceleration of the each frame, which can be measured or apparent acceleration. So we have to take into account that they are changing with the time as well. So it's going to be the second derivative of the position. From the previous slide we had this one, so if you get the second derivative of that formula, you're going to come with this one here. We also have the rotation element. Without going into details, this can be put in terms of the angular rates skew symmetric as shown here. So you don't need to prove it, you just need to understand what are the terms. Now I'm going to ask you to write these questions, so don't worry if it's too complex for you. So the first three terms respectively explain centrifugal effect. We all know about centrifugal effect. Then we have Coriolis and ellipsoidal force. So the next slide I will explain you what is solenoid force. So imagine you have a cannon which is placed on a rotating disc. So cannonball fly in a straight line since no force acts on them. So let's have a look. So you can see the cannonball are going straight since there is no force. Now we will switch to the disk's frame of reference. Then you will see the cannonball path will seem to be kept. Let's have a look. So two frames are moving in respect to each other. You can see they are no longer a straight line. They looks like a curve. Continuing, we want to see how this movement can be visualized using the arrows, which is Coriolis, centrifugal, and then total effect. So now we want to look at the same scene again with the force visualized as arrows. The blue one shows the Coriolis, green one is centrifugal, and then the white one is the total. Let's have a look again. So blue one is the Coriolis, green one is centrifugal, which you can see, and then the white one. In the second example, we are looking at the pendulum, which is going left and right on the rotating disc frame. Again, we're gonna have the horizontal force in a direction of the swinging of that pendulum, which has been shown by the red arrow here, and you see it's gonna change during the swinging of that pendulum. Good. So if you want to see the centrifugal and Coriolis effect on this movement, basically centrifugal effect is the opposite sign of the string or swing of that pendulum. Then we have the Coriolis effect, which has been shown by the blue vector. So in this case you can see I'm looking at with respect to the frame of that reference. So if you map the footage of that movement, it's gonna look like a circle. So let's have a look at that. That circular motion can be visualized in the inertial reference frame. You can see looks like a circle. As the frame is moving, the reference frame also is moving with respect to them. Looks like a circle in the inertia of the frame of the reference. Now let's do the same thing, but this time we are consider the pendulum's period is 33% smaller, and then we try to see how centrifugal, Coriolis, and total force looks like. This is the example, but if you map the footage this time, it's no longer a circle, it looks like this picture here, which a flower to me. Hopefully that shows you what is the centrifugal and Coriolis effect is, and how it looks like in the frame of the object as well as the frame of the reference. So if you are at rest and acceleration is 0, the force is basically exerted on the object in opposite direction of the gravity. But imagine you're in an elevator and you're accelerating up, so you're going up. The acceleration you feel is in opposite direction of gravity. So I have acceleration is applying in the opposite direction. What you feel is you sense both the acceleration of the lift and the resistance to gravity, so you feel heavier. In the same way, if you're accelerating down or falling, the acceleration will be applied in direction of the gravity, so you're gonna feel a lessening of the force. Now consider an object at rest in the Earth-centric Earth-fixed frame. In that case, the velocity and acceleration in that frame are both 0, and the velocity and acceleration in the inertial frame realized in Earth-fixed Earth-centric frame are 0 as well. So if we consider the previous formula we have, so we can say since we don't have enough velocity or acceleration because the object is at rest, the last three terms gonna be 0. So I can rewrite that as this one. So it can be written as this one here. So acceleration is equal to basically centrifugal effect. Since the specific force sensed when an object is stationary with respect to ECEF reference frame, we can refer the acceleration due to gravity as this formula. The specific force sensed when an object is stationary with respect to the ECEF frame, which is referred to the acceleration due to the gravity, or G in here. Again, we don't need to prove this formula, but we need to be able to understand each term. So the first term is the gravity we measure, then the second term is the centrifugal effect, as we know. On the surface, the second term is approximately 1/300 of second, which is 0.034 roughly meter per square second. but in orbital application it becomes more significant. In inertial navigation system, we care about velocity, position, and heading. If you kind of remember from the physics, we can write velocity as an initial velocity plus acceleration times t. And then we had a similar thing for the position or displacement of the object, can be written as initial velocity multiplied by time plus half of the acceleration squared t. So we can remember this one, sorry, this is v. So this is in the case that your acceleration is constant, but in real or inertial navigation system there is no such a thing as a constant acceleration. Acceleration is changing during the time. So we have to consider the time derivative of these two formula, which can be written as these two. This equation can be evaluated in each component, actually in three orthogonal dimensions, as we know, x, y, z. But just now imagine we are constrained by two-dimensional plane, which is perpendicular to the gravity. So we only need to have two orthogonal accelerometers in the plane. In addition, we are assuming that our sensor frame is perfectly aligned with the body frame, so there is no difference between the S frame and B frame. If we imagine all those assumptions, the IMU is basically either stationary, there is no movement, or is moving with the constant motion until we decide whether we want to decelerate, accelerate, or brake. Good? Let's have a look at the simple example. When you're driving on a car and then you want to turn left, first you need to brake or decelerate, then we will go left and then we accelerate back again. Let's have a look how it's gonna look like in the... Let's start with a simple example. Imagine you're driving in a car and you want to turn on a road. So you first need to decelerate, so you're braking. So the acceleration shown on the right hand side is in the B frame. So what's happening is you will feel when you decelerate or brake, you will move forward in the direction of the front of your car, and then when you are turning left, acceleration is into direction of the left, but you will feel that you move to the right hand side. And then as you go through the road and then you come back to the road, trying to accelerate again in the direction of the road. So again, acceleration is into the front, so you're accelerating the direction of the road, but what you feel is like you will force back to your seat when you are trying to move faster. This diagram on the right hand side basically show you the acceleration in the B frame, but what we need for navigation purpose is the acceleration in G frame. So on the right hand side I'm going to show you how the acceleration looks like in the G frame or geodetic frame. So as you are decelerating, the acceleration is in this direction. As I'm turning left, you see acceleration start to change. Good. As I'm accelerating back, then acceleration is going to be in direction of the travel. So this means before the accelerometers can be of any use, we need to update the frame relationship continuously. So we need to understand what is the relationship between the B frame and G frame. This is one of the purposes of gyros in the IMU, so we can get the transformation from the B frame to G frame. In this case it's very simple, we only need one gyro in the aligned with the z-axis to get the rotation or the position of the heading, but in real world we need to have 3 gyros in each axis to get all the rotations. Actually, gyro do not give us the bearing or heading directly. They only measure the rate of rotation known as the angular rate or omega, which we've talked about that before. Like before, if I have the initial heading, which is this term here, and then if I can get the time derivative of the heading as the time is changing, the heading also is changing, so I can get heading after the period of the time like delta t. So this is somewhat simplified version of what it is in reality. In this example, we assume that the z-axis of G frame and B frame are coincident, so I can write E and G. However, this is not the case for acceleration. They need to be transformed using the rotation we discussed earlier. Now let's have a look how navigation process is working. First of all, we need to have some sensors, which are gyros and accelerometers. So we have IMU sensors sitting on the three orthogonal axes of the body frame. Then we need to have the initial position. So initialization itself is a complex procedure, but we assume that we have the attitude, which is orientation, velocity, and position at a given time. Let's put aside that procedure for now, and then we will come back to that later. So we have the initial position. What's happening next is we get the attitude update. How are we going to update our attitude? Using the obviously gyros sitting on three axes, we can get the angular rate measurement, which is omega x, y, and z. So we can get the angular rate at x, y, z direction, and then we can multiply that angular rate by the sample period, which is 1 over frequency. This gives us the attitude update, which we need to add that value to the initial value that we have, so we can get the attitude update, which is the orientation updates from gyros. The next step is we get the acceleration measurement from the accelerometers. The next step is acceleration will be measured in IMU sensor, and then they will be transformed to the G frame. I've shown you we are looking at the acceleration in G frame, not B frame. To do that, we obviously need to have the angular rate of change from gyros to transform the acceleration into the G frame. Once you've done that, the next step is we need to update the velocity based on the transform acceleration from the previous step. So we use this acceleration and we use the sample period, and we can update the velocity. However, we need to be careful about the acceleration we will be given using the sensor, because unfortunately the instrument cannot differentiate the acceleration due to the movement of the vehicle from the acceleration due to the gravity. If we somehow can find the acceleration due to the gravity and subtract it from the total acceleration, we can get the acceleration only due to the movement of the vehicle. But finding that acceleration due to the gravity is not easy, as we know from geodetic surveying. It's going to change due to the elevation location on the earth. At this stage, we can incorporate a gravity model to make this correction and correct actually acceleration measurement due to the gravity. Now, once you have the attitude update and then you have the velocity update, we can easily get the position update in the correct frame and elapsed time. So this gives us the navigation solution. Then it basically will go back to the first option and then repeat it. How often do you get that navigation solution? It basically depends on the update rate, which affect the accuracy of the solution as well. How it's going to affect? Remember the IMU averaging the value over the time and give you the average value. If the time period is shorter than the rate of change of the value, then everything is okay and the averaging doesn't really matter much. But in very dynamic environment where the value is changing dramatically quickly, then the average value doesn't reflect the motion of the vehicle or the body. So then that creates some problem with the accuracy of the final solution. As I said, this can happen in very dynamic environment, or if you have lots of vibration, this basically not giving you the very good result as a navigation solution from inertial navigation system. Now let's have a look at each of those steps in more depth. Attitude update, we've talked about that. I told you in the attitude update we get the angular rate of change from gyros, and then we multiply by sampling time, which is 1 over frequency, and then we can get the attitude updated. In reality, to update the attitude in the E frame, E frame is Earth-centric, Earth-fixed frame, we need to account for two terms. The first one is the rotation of the B frame or object frame with respect to the inertial frame or I frame. The next one is the rotation of the Earth-centric, Earth-fixed frame with respect to the inertial frame. We know ECEF or Earth-centric, Earth-fixed in relation to the inertial navigation system is changing with the constant rate of the rotation of the Earth. So luckily we can consider that constant rotation and is very small, so we can basically multiply everything by that rotation and then get our position updated in respect to the Earth-centric, Earth-fixed. So the updated transformation is the original or the previous solution times to the, so if you have the initial attitude, which is this one here, we can simply get the new or updated attitude using this equation. Remember, this term in the equation can be written as this matrix. The omega is the omega values are the rotation rates measured by the gyros in the IMU system, and the last term here is accounting for the frame Earth rotation. Again, you don't need to know this formula by heart. All you need just understanding the terming and how it's working. The next step is force transformation. The forces we are measuring in the B frame, we have to convert them into the inertial frame, and then we can bring it to the desired frame, which is Earth-centric, Earth-fixed. So to do that, we can use this formula written here. As you can see, we have a transformation matrix which we can transform from the B frame to the E frame. Good. However, to account for the fact that the orientation is updated at the end of the time period rather than in the middle, we need to get an average of the start and end of the time period for the transformation matrix. So we can rewrite that formula as this one here. So having that transformation matrix, and then if we know the force at the B frame, easily we can convert the force at the B frame to the force at Earth-centric, Earth-fixed reference frame. Then the next step is velocity update. We've talked about the velocity update. Now we're going to look at more mathematical term of that. Again, we need to have the initial velocity, which is shown by negative sign here, and then we have the updated velocity. To update the velocity, we have to go back to the previous examples we had that we've talked about centrifugal and Corollary's terms. If you kind of remember, because the rotation of the Earth is constant, we still need to consider the centrifugal and Corollary's terms due to the rotation of those two frames in respect to each other. So if we consider those terms, and then we also need to separate the effect of the acceleration due to the gravity, as I've taught. So we have to apply the gravity model, which is basically function of the location R here. Then we can calculate the updated velocity, but just remember this is just the approximation because we need to rely on the previous location to calculate the gravity term. So which is probably not reflecting the current or present location of the object. So that gravity term is not quite what it should be, so we only can have the approximation. So the last step then would be the updating the position. As the velocity, from what we know, is the time derivative of the position, if I have the change in the position, which we call it velocity, and then if I multiply that by the time period, then I can get the changes in the position. So basically what we are doing here is I have a velocity while I'm just measuring the, I think this one should be plus, sorry. So what I'm doing, I'm measuring the, or averaging the velocity between the start and end of the time period, and then I multiply by the time period. This one is the time period. Good. Then I will add that to the previous location of the object so I can get the updated position. So I know the mathematical concept might be difficult for you, but as far as you understand the procedure, that would be enough for us to know. So once we have the position updated, it gives us the navigation solution, and then this process is gonna repeat it. It's like a loop. So we're always having the updated solution, we are coming back to the previous one, so it's just a loop going from the previous solution to the updated one, and for each frequency. So we're gonna have the sampling rate, which it gives us the updated navigation solution for each sampling rate. So in order to get the navigation solution, we've told that we need to have initialization, which gives us the position, velocity, and attitude and heading for the first position or first solution. Obviously, position is so easy. We can get the first position using the GPS or GNSS measurement. So it gives us the position for the known points, or the first point, obviously. So if you're, for example, starting your UAV, the first position can be get from the GPS, and then using the IMU measurement, it basically gives you the navigation solution based on the velocity, acceleration, rotation, around each axis, which is pitch, roll, and yaw. So position is easy, we can solve it using GNSS. The next step is we need to solve for the velocity, because it's the stationary vehicles, we don't have any V, so V0, this one can be get from GNSS. Attitude and heading, they're a little bit harder than velocity and position. We need to have the first solution for the pitch and roll, which is a little bit simpler, but heading or yaw is a little bit difficult to get. Let's have a look at the first two, which is pitch and roll. For the instrument, which has the IMU and is self-aligned by leveling, we can assume that the only acceleration on that instrument is based on the gravitational force, which is in direction of the gravity, obviously. Having said that, we can write the force of the gravity, if you kind of remember this formula we've had before. So this is the transformation matrix from the gravitational force in geodetic frame to basically be our object frame. We had that transformation matrix before, but it was in this form, and we are only using the last column. It was 3 columns, we are only using the last column. Reason for that is we are only considering the pitch and roll, which is phi and theta. Good. So we don't consider the side or heading yet. Good. We want to solve for these two. If I consider the last column of that matrix, and obviously I have to reverse the sign because I'm transferring from G to B, not B to G, then I can get this matrix, and from that I can solve theta and phi. Again, it's not something we need to know, but you need to understand the procedure. So from this formula or leveling, we can basically get the pitch and roll solved for the initial position. Having solved for pitch and roll, the next element would be the heading. For the stationary IMU, we know that we only can sense the Earth's rotation, which is in direction of the Z in the centric Earth fixed frame. One way to go is to put the pitch and roll in the matrix we had, which was C. I can write it here, knowing the matrix of CPG, and if you have pitch and roll, then we can get the heading. This is one way to go. This method is useful in theory, but in practice, any vibration is probably create rotation rates of much greater than the Earth's rotation rate. And do you remember I told if you have that causing the problem for the average value you will get from this method. And if you want to have a good solution, you probably need to leave it for many hours. So this is not good for us. Another method which we are using is we get the indirect gyro. Another method is gyro compassing. How it's working basically? First, using the indirect gyro compassing, we get the relative attitude solution, which has been transformed into the inertial reference frame. Since the gravity vector is not parallel to the axis of rotation of the Earth and is changing as we go through the time, so imagine if we consider in the 1 day period of time, it's going to sweep to the cone shape, and its time derivative will be a vector parallel to the rotation of the axis of the Earth, which is this one here. So looking at the change of the gravity vector in the inertial frame gives us the direction or heading. So normally it takes 2 to 10 minutes to calculate the suitable heading for the initial position, and then it's much quicker than using the formula that I've explained here. The error in an inertial navigation system's position, velocity, and attitude solution arise from 3 different sources of errors. There are errors in the instrument itself, which can be related to the accelerometer and gyro measurement. We've talked about that before, which can be categorized to the biases, scales, and random noise. We also have errors in initializations process, and then we have some errors related to approximation made in the processing. So based upon that, we can categorize that inertial measurement units error into 3 different categories. We can say short-term straight line errors, we do have medium and long term, and then we have maneuver dependent errors. Let's have a look at the first one, short-term straight line error. The simplest INS error propagation scenario is that we have short-term propagation when the host vehicle, or it can be your UAV platform for example, is traveling in a straight line at a constant velocity or speed and remains level. So in considering this, we only have the short-term error propagation. So we don't have any effect of curvature and rotation of the Earth because we're assuming we are going through the straight line. So if we consider this, the position error grows with the constant velocity. So what it looks like is this one. So you can see errors in the position in terms of velocity. So it's like a linear term. So the blue one shows the velocity error during the time, which is linear. This affects the positional error, which is proportional to the time squared. So it looks like the red curve here. We've learned that the bias in accelerometer can affect the velocity in a linear term, and then it can be proportional to a square time on the position error in the gyro. If you have the bias error in the gyro, that will affect the attitude error, which basically at the end of the day causing the errors in the force transformation. If I want to visualize that for you, I can draw it like this is the force that we've measured, and then we know that the true force should be this one. So this is the calculated one, this is the true value, and then this is due to the attitude error, which I can show that with this one. Good. So I have the error in attitude, which causing the error in the acceleration. So I can write it as this one. And then we call it acceleration error. Error due to attitude error. So if you have any error in attitude, that will affect your acceleration, which can be calculated using this formula here. Because we are moving with a constant speed, assuming that the instrument or your vehicle is leveled, the only acceleration we have is acceleration due to the gravity. So the effect of acceleration errors is going to be in X and Y accelerometers. So after integration, we can say that this means that the velocity or error in velocity is the proportional to the time square, and error in the position is going to be time cubic. So we're going to add, remember from previous one, I've told you error in the velocity of beta b, and this one is gamma at time t, is linear. So I told you you can write something similar to this. So it's linear with the time, but if you're taking into account of this acceleration error, it's going to be proportional to t squared rather than t. The other major source of error in this scenario is noise. If your system is well designed, usually all the noise errors would be white noise, which they have the same intensity for all frequency, and then for each frequency it basically has the normal distribution. But because we are not living in the ideal situation, we always have different scenario. So the standard deviation for the accelerometer and gyro noise in this case, they are related to the time, so they are time dependent, and they are growing with the time up to the limit of 2.5. So they are growing, but once they get to 2.5, they stay at that level. The second type of error are medium and long-term type of error. These type of error are small to start off, so they're small at the start and they can be ignored, but over the time they grow with the scale. They usually have the sine shape function. Example of this type of error is error due to the gravity model or initial position error, which they change periodically with the frequency, which we call the Scheller frequency. This frequency depends on the latitude and elevation. The reason for that is as the strength of gravity field is changing based on the distance to the center of the earth and latitude. So basically this affecting the period of the Scheller frequency. Another example of that would be horizontal position error due to the initial velocity, accelerometer bias, and initial attitude error, which follow the sine shape error as I've shown here. But remember, error due to the gyro bias is rising linearly and then it start to flatten off after an hour. So we have to consider this. So gyro's bias basically is more complex than the other type of errors we have in INF. The last type of errors is maneuver dependent error. So far we assume that we have the constant velocity to allow us to simplify the effect of attitude errors. Like we don't consider the heading error, we're just looking at the pitch and roll and a horizontal positional error. But when maneuvering, the cross product creates error effects in all accelerometers due to error in the gyros. The advantage of this type of error is basically it can be balanced out over successive change in direction, but unfortunately this is not the case for a circular or oval trajectories where the gyro scale factor and cross coupling error will produce the attitude error that will grow with the time. So it can be balanced out, but not always. It depends on the basically your trajectory's shape. If it's circular or oval, we can't really balance out this error. As we saw earlier, so error in calculated position and orientation given by IMU measurement, they will grow as we go through the time, so they become larger. So we have to find a way to minimize those sources of error. One way to go is to integrate GNSS observation with IMU observation. So in reality, GNSS observation, they have low temporal resolution. They only can be updated every second, but IMU can be updated the frequency is 1000 Hertz, which is we can have 1000 observation in 1 second, which is much more than GNSS. For this to work out, we need to have some type of mathematical formula to combine these two together, which we call it Kalman filter, which I'm going through that in the next slide. What Kalman filter does is basically assuming that the actual motion of the vehicle is the black line here or black curve, and then the measurement we have from IMU is the blue one. So if we have the position from GNSS every second, you can see that we can correct the position we've measured using the IMU and integrate that position with GNSS. We can correct it to the actual measurement, so it gives us better estimation of the actual motion of the vehicle. Imagine we are tracking an object and we are interested in where it is and what is its velocity. To make it simple, we only consider one dimensional, so we consider the position of the object in respect to the velocity. As you can see in the picture, because the position and velocity might have an error, so considering the normal distribution, we can say the position or true position, it should be somewhere in here. When it gets darker, it means that it's more likely that your point be in the darker area, and the middle of that is basically showing you the best estimate of position, which shows by mu. In the case above, the two parameters are uncorrelated, so we imagine there is no correlation between the position and velocity, but in reality they might be correlated. So when we are constructing the matrix of variance covariance, we need to consider the covariance as well. These are the uncertainty in position and velocity, and this one is the basically cross correlation between the position and velocity. Again, we can write down the position for any points here as a function of position and velocity, so R and V. Imagine we want to predict the next position for the best fit. The prediction works equally on all possible, so it's gonna come from this to this. This is the prediction, and basically our prediction, which is Fk, this is our prediction. At time k, and is basically map all possible states of the time k1, which is the red cloud, into the blue cloud, which is at time k. Just if you want to write the formula for that, the only thing which is added is this one. So consider the previous one was only R and V. Obviously, if we are talking about the k minus 1 time. Then we added the change based on the velocity, so which gonna be the fk, which is our function. So if we are moving with the constant velocity, it's gonna change our location to the blue area of blue cloud here. Considering the covariance matrix we had, it is a standard result that we multiply every point in a distribution by a matrix fk. Good. And then we can construct the matrix of variance covariance for the new position. This is when we have only the velocity, constant velocity, but just imagine we want to have acceleration as well. So we might be accelerated using a constant acceleration rate of a, for example. Then the whole scenario will change and we're gonna have different formula. So if you look at this one without having any acceleration, but if I'm adding the acceleration, I'm adding the acceleration term, which is this matrix with the constant rate of a. So I can rewrite that formula into this, and there are two new terms here. The general term of bk, this one here, is the control matrix, and this one is the control vector. So by adding the acceleration, constant acceleration to our object, this formula can be created. Same thing for covariance matrix. For covariance matrix, we added the extra term, which is Q, which is the new uncertainty related to the environment if we have acceleration. Good. So the final prediction from this can be the blue cloud that I've shown in the previous one. Good. Now imagine, rather than just relying on the first estimate and prediction we had, we might have some other way to measure the velocity and position. Maybe we have some sensor that we can measure it. So for each of those possible position and velocity that we had before, then we can mapping them into the sensor space by the matrix of hk. So the formula we've had, it can be rewritten as this one. Same as before, nothing is perfect, so our sensor also might have some error associated with them. So we need to consider extra term for the measurement error in our matrix of covariance. Now we are having two sets of distribution, which leave us to having two estimates of the value both with own associated uncertainty. Good. Now the question is, which one is the correct one? How are we going to find out which one is the correct one? The example is, if you, for example, have two horses, or if you want to bet in the horse races, you get excited and you want to bet, and you have two horses. The first one, you have the 25% chance that that horse is going to win. So the probability of the winning of the first horse is going to be 0.25, which is 25%. I have another horse, which is probability of the winning is 33%, which is a little bit higher. But you always have a chance that both horses are winning. So in this case, what is the probability that they both gonna win? So it's gonna be in statistical. If you have two probability and you multiply them together, it gives you the probability of that both happen at the same time, which is usually less than the two probability or uncertainty that you've had at the moment, which is in this case is 8% that both of your horses are winning. Same thing can apply to this scenario. So if I have two normal distribution and two best estimate value, which is mu, so if I multiply them together, it's gonna be the probability that the both are happening. So the best value can be estimated using those uncertainties. Same thing can be, so from this I can come with this formula. What this formula shows you, the first one is the k value, usually between 0 to 1. The next one is the best estimate value from these two probability, and then the uncertainty associated with that. Usually this uncertainty is less than the uncertainty of two other estimates, and the k-value is usually called Kalman and is less than 1. You might say, so what? But how is going to relate it to our assumption? If you can remember from previous slide, we had two probability or two area that we think our best estimate is going to lies there. The first one is the green one, the next one is the purple one. So you might say, what is the best estimate? So the best estimate from the first function is this one, and from the second one is this one. So we want to find a way to combine these two estimates together to get the best value. So we can use the same formula we've had in the previous one. Applying that to our scenario, we can get the best estimate of the position as well as its uncertainty using this formula here, which is written here. Obviously you can make it a little bit easier by getting rid of some of the common terms to get a modified version of the k prime and x prime as well as the p prime. Good. So it gives you the new best estimate, which is stated as the x prime. It gives you the basically is uncertainty related to that, or matrix of uncertainty with using the p prime, and then obviously it gives you the k value, which is somewhere between 0 and 1. Obviously we are not too worried about the math behind that, but we need to understand how it's working again. Kalman filter can be applied to integrate the IMU with GNSS measurement. Obviously the math behind that is a little bit complex, but what I'm caring for you guys to know is mostly to understand what is the procedure. So we come with the initial position, which has been shown here, and then we use the IMU measurement of the position, velocity and attitude to predict the value for the next position. Then once we've had the prediction from the IMU, basically this prediction will be used as a previous state for the next prediction, and then we keep looping until the GNSS measurement become available. So we know that we do have two different frequencies, so you might have 1,000 observation for 1 second of IMU, but we only have 1 hertz frequency for GPS, which means that we only have 1 measurement per second. So after a second, when GNSS measurement will be available, then we use the GNSS measurement to update the position and velocity that we have predicted from IMU. We also trying to have better estimate of the bias and attitude, and then once we got the updated position, this process will be continuing. What do we expect from integration of the IMU and GNSS? So it's basically like any other surveying techniques that we have. You get what you pay for, obviously, and then you can use different GNSS techniques. We know that RTK, for example, give you better accuracy than simple point positioning or PPK same way. So these different techniques also is affecting the final accuracy we can get from integration of GNSS. Table here shows you the different accuracy you can get for the position and height based on which techniques you will use. The last two columns here shows you the quality of measurement after having 1 second without differential correction. So we are having 1 second without differential correction, and after that is starting to have RTK, for example, and PPK, which gives you the accuracy of 0.5 meter and 0.3 meter horizontal accuracy respectively. You need to remember these are sigma. Sigma at 68% confidence level. So there is 32% chance that our measurement lies outside this accuracy. So this is the end of this lecture. Hopefully that helps you to understand some of the concepts related to the INS. Please ask me any question you have in the forum, and I'm happy to answer your question. Thank you.